Now we understand that equilibrium is very important for molecular dynamics to happen. But as you know, not all systems are in equilibrium. Some of the systems are also what we call chaotic systems. And there are methods which is called nonlinear molecular dynamics, where you can also predict them. But for the discussion of this course, we will confine ourselves with the equilibrium molecular dynamics, with the ergodic theorem being applied. So, the systems are ergodic because the time average and are equal to ensemble average. Those systems which are non-equilibrium, they are non-ergodic systems as well. So, we are going to look at some examples later on non-ergodic system. But let us start with, again, getting back to our programming here of the molecular dynamics course. So, in molecular dynamics software, now we are beginning to look at the trajectory for the equilibration of the system. So, we begin with a main time loop of the simulation with n times is equal to 1 to max kb, and then kb is equal to kb plus 1. So, we are increasing the time step every time we can finish the loop, and we are calling 4 distinct subroutines. So, one is calling prediction, which is 5th order predictor corrector. Then based on the predicted trajectory, which is telling us the position of particle at time delta t depending on the time step here, then we are going to do evaluation of the forces, and that will give us the new position based on the potential energy parameter. So, one is giving this finite difference trajectory moving forward, another one based on those position what forces are generated, and based on those forces you can also create evaluation of the times of the location of particle. Now, difference between predicted and evaluated, now we are able to calculate the correction step, and that correction step is distributed over all 6 terms in the 5th order predictor corrector, including x 0, and then we also call for neighbor program, because we only want to calculate forces between the pair potential which is invoked for the neighbor list, as we discussed earlier. So, now let us look at the 5th order predictor corrector. As you know, we earlier looked at these equations, rather formidable equations here, where k provides the predictor corrector step or expansion, and then I is number of particle, x I, t is the time. So, if you look at the predictor step is calculated x I 0 coming out of x I 0th order, 1st order, 2nd order, 3rd order, 4th order and 5th order predictor corrector steps. So, these are all the parts of the expansion of Taylor series up to the 6th segment, and we are looking at 3 dimensional. So, we are looking at 3n degrees of freedom for each particle. So, once you calculate that, then you can calculate the predictor. So, it looks very similar to the formulation that you saw earlier. In this case, essentially now this is converted into program. So, if you look at here, we start with x 0 I is I 1 to n p number of particles, but now we have all these Taylor series expansions x 0, x 1, x 2, x 3, x 4, x 5. Now, we calculated for all 3 x dimension x 0, y 0, z 0, then we go to x 1, y 1, z 1, x 2, y 2, z 2, x 3, y 3, z 3, and x 4, y 4, z 4. So, now with this 5th order predictor corrector, and we already know the calculations of these, we are now able to initialize the force array. So, we start with f as all array as 0, and then we calculate the positions first. So, once you predicted the positions using 5th order predictor model, then as you know, we are going to calculate the force in Lennard-Jones pair. We already initialized force as 0. We will use the Lennard-Jones potential. Important point here, as you are seeing on the slide, is that we calculate only the nearest neighbors, and this neighbor list is kept with us. So, now going forward, how do we calculate the force? As we saw earlier, we are going to go over double summation loop because we are looking at particle I and particle j. So, for each one particle, we are doing all j particles, then we go to particle 2, then do another j loop with all rest of the particles, and but j is not equal to I. This is how with this double loop we are able to calculate all pair potential, pair differentiation, and so these pair forces are also coming out. And then because f I j is equal to f j I, we do not have to calculate some of these terms as long as f I j is equal to f j I. That way we do not have to over calculate, and with that understanding now we are going to evaluate. So, evaluation is very simple. You are essentially using the Lennard-Jones potential function, and from that you can calculate the potential. So, here we are calculating R6 and repulsion force. So, we have a repulsion force parameters, and then we are looking at the position vectors, and with that we are able to calculate forces for all condition for I and j, and in x direction, y direction and z direction. And when you do, then you can create the total energy and based on total function that we call in. So, these are some functions called by the subroutine. Once it calculates that, it continues to the second loop, etc., and it calculates the entire evaluation of the forces for that neighbor list and for that pair potential. So, if you look at now that you have evaluated that, you are ready to do correction step. For correction, you need to understand that the force that is calculated based on the new positions, that gives us an idea about based on the potential energy, we can calculate the new force, and the new force will provide us the new location of the particle. So, we have predicted as well as evaluated position of the particle, the difference between them in again in 3 dimension. So, we have 3n degrees there. In that EI, which is the error function here, as you look into your slide, is essentially look at the second order part here. We are just looking at second order, but it is done for all orders, first, second, third, fourth order for the fifth order predictor corrector. So, if you look at here, we are then going to do xi 2, which is the second order, fi over mi delta t square by factorial of 2. So, now, this is what is the evaluated, this is the predicted, and the difference between the two is the error function. Now, we apply correction to the to this particular. So, x I k, again whatever order we are using, with that we are going to go into minus the correction term. So, this is the predicted one minus the correction one is the real position of the particle based on predictor corrector, and we already saw those coefficient that are created based on the differentiation of the first order, second order, third order and fourth order in order to create our calculation for the real positioning. So, with that understanding and distributing error in all fifth order predictor corrector, we get very accurate trajectories, and that is where we then apply this corrector into all. Again, we are looking at all different expansion of the Taylor series x0, x1, x2, x3, x4, x5, y0, y1, y2, y3, y4, y5, and z0, z1, z2, z3, z4 and z5. And this is where the difference between the predicted and the evaluated position of x2, y2 and z2 are looked at. We are looking at the second order force calculation with the Newton's laws of motion. Now, once we distribute it, now we have a corrected trajectory. Now that we have new positions, now we need to make sure that we apply the periodic boundary condition here, because the atoms have moved. Some of them may have gone outside the boundary. So, we are if this is more than certain half of the length of the box, which we are applying on both sides of the atom, then it is going to add another half to it, so that it comes back from the other side of the box with the same velocity. So, this is where you also correct for what we call as periodic boundary condition. So, you took any artifact out, and now you are able to calculate the bulk properties. So, that is an important factor, that the way we apply this periodic boundary condition is again looking at the box delta x, delta y and delta z displacements in your code, and then you look at all the position x0, xy and z0 initially, and then we apply this periodic boundary condition that if x(x) is less or equal to 0, then x(x) is equal to x(x) plus cube. So, we are adding that half of the cube or subtracting half of the cube length, which is the size of the cubical box, and that is why we, by applying that to all 3 dimensions, we are able to now get the new positions with the idea that now we apply the periodic boundary condition. And then in the force calculation, we will also have the minimum image criteria. So, we only calculate the pairs with the periodic images with the which has the least distance from the central atom. So, by this we are now coming up with a good recipe here that we can create the whole molecular dynamics simulation and the displacement vector, and by applying that, now we can look at the equilibrium steps, and I have looked at like 100 time steps. You are looking at the time step in femtoseconds, and here is the total energy, here is the temperature, which is constant, distance between that is changing. Now, you look at the energy, this is the total energy. If you look at here, now we are seeing that it starts from minus 4.532, but at the end it is settling down to minus 2.81. So, this and also is fluctuating between minus 2.8 to minus 2.7. So, this is where we are reaching an equilibrium position, because energy is conserved. We look at that particular energy segment to make sure that we are getting to an equilibrium situation. And again, I am just showing you 100 time step, but you could take 1000, 2000 time step until you are satisfied that the pressure that there is the energy parameters are constant and it is conserved, and that is your first indication of equilibration step. Now, you are ready for the real calculation of properties. Thank you.